Today we will start with somehow the second half of this lecture series, namely we will start with the easy quantum groups. So these are some quantum groups which are given by some combinatorics. So in some sense the first 4 lectures was some general basic on quantum groups, and now there comes 4 lectures on easy quantum groups. So somehow now this is a cut, and if you missed the first 4 lectures you can start with this lecture. And it starts with Tanaka Crying. So this is still something from chapter 3. So this is a little bit from chapter 3, but then we will start with these easy quantum groups. So what is this Tanaka Crying? Well, I said that there's this Pontryagin duality. So if G is compact and abelian, then the double dual of G is isomorphic to G. So in this sense, G may be reconstructed from the dual. Okay, so we have this dual group. So now what happens if the group is compact but non-abelian? And this is classical Tanaka Crying. So I'm not at all an expert on group theory. I'm just mentioning these results here. So there you can reconstruct G from the finite dimensional unitary representations. And these are represented by intertwiner spaces. So these are given by some linear maps T, such that you have some intertwining some intertwining relation where U and V are representations. Okay, so this is some classical Tanaka Crying theory. As I said, I don't know too much about it, but what we should notice at this point is that somehow you want to extend this Pontryagin duality to some non-abelian groups, and this is what these people did, and they used some intertwiner spaces. And now, Woronovich he also has some Tanaka Crying for compact quantum groups, and this is somehow that this is also given by representations and some morphisms in between, and these morphisms they look exactly like these intertwiners over there. Okay, so a bit more precise. This is now what I will sketch now, and this is the following. So we take a compact matrix quantum group. So this is, so usually when I wrote these compact quantum groups, I wrote A delta, saying that we have an algebra and the co-multiplication. Now for these compact matrix quantum groups, I will always write AU, because this is the critical point, these generators Uij. And recall that these Uij, they determine my delta immediately by saying that Uij is mapped to this matrix multiplication like product. Okay, so knowing U is the important thing, delta comes automatically. So we take a compact matrix quantum group and we denote by rep of G all finite dimensional unitary representations. And by more of maybe V and W, this should be all linear maps that intertwine these two representations. Okay? So this is the space of intertwiners. And yeah, here, so V and W are from rep G, and since they are finite dimensional, they are on some Hilbert space, so matrices over A, and I can also just write it as this is the corresponding Hilbert space. Okay, so where V is in V of HV tensor A and so on, and W likewise for W. Okay, so this is my setting, and then this has a certain property, namely these objects together with these morphisms, they are a concrete monoidal W star category. So what does it mean? It means this morphism is closed under taking tensor product. So this is if we have one intertwiner and a second one, then also the tensor product is an intertwiner. Okay. Okay, so I will write down a list of properties, in fact a long list of properties, and while writing it down you can just check in your head that these things are true. This is really easy. I mean, if you for instance want to check that this is an intertwiner here, you apply T1 tensor T2 to U1 tensor U2, which means I apply T1 to U1, T2 to U2. Now this intertwines according to these relations, and then I have something like V1, V2 times T1 tensor T2. Okay, so this can be immediately checked that this is true. It's even easier for the second one, which is composition. So this is if we take intertwiners T1 and T2, then also their composition is an intertwiner. It's closed under involution. So if T is an intertwiner, then T star is an intertwiner for the converse morphisms. The identity is in these morphisms. And then we have some other technical conditions. Which are not too important for us for the moment. And the last one is that there's some representation 1 on the complex numbers. Okay, so a list of properties. For us, only the first 4 will be important, but okay, so this is the definition of concrete monoidal W star category. So concrete, because you're always working on some concrete Hilbert spaces. Yeah, and there's some category language which makes sense to call it a concrete monoidal W star category, but well, for us, the important thing is that when we start with the setting, we get this list of properties. And we have another property, namely that there exist conjugates.
you consider as objects equivalence classes of
no, really these elements. So these.
An object consists of a representation and a Hilbert space.
Yes.
So the sixth equality, that is the associativity of tensor product.
Yes.
That is up to isomorphism or the natural isomorphism.
Yeah. You identify these tensor products of the Hilbert spaces. Yeah.
Okay. And another, is the set of all finite sets a set?
You mean the set of all these finite representations?
Yeah. Set of all finite sets a set, because there will be as many Hilbert spaces as finite dimensional Hilbert spaces as
you have all representation are having the same
Yeah, there's some issue there. Volonovich mentions this in his papers. So this is a Tanaka Crying paper, and there's some remark on this set theoretical thing, which I didn't want to repeat here, but you can check it there. As I said, I guess he thinks that this is some subspaces of all of the same Hilbert space or something like this. Okay, and furthermore, to each representation we have a conjugate representation. Is this too low? Can you see it if I write in this line? It's okay? I'm always a bit confused with the Indian way of shaking heads, so this means it's okay, right? Yeah, okay. Furthermore, for all V, there exists a conjugate and U and U star generate rep G. Okay, so this is a long list of properties that we have for this representation, and yeah, well, for the proof, as I said, so these properties, if you just check it step by step, this is really you can do it by hand.
The last statement that you made for V, you define V bar and then?
Here? This is,
that's fine.
that's Vij star.
After that, and
The set, so the fundamental representation U and its conjugate U bar, they generate representation G. Yeah. Sorry?
You start from cats from the beginning.
From a Katz quantum group, you mean?
Yeah.
No, I think this is for a general compact matrix quantum group.
okay.
Because this one is not unitary.
Yeah. And I think
you need either to assume this is cats from the beginning and this one is unitary,
Mm-hmm.
the V-bar, or to say the V-bar you can characterize like this. You say there exists a unique V-bar such that one
right.
is included. There is isometry from one to V tensor V-bar.
Okay.
And then this equals for non-cats.
So you.
Assume cats.
Yeah. I mean, Volonovich formulates his theorem for also for non-Katz types.
Yeah, but this won't be unitary. This V bar. That's the
This one.
Yeah, so you have to do it.
Yeah. Okay. So I mean,
Define like this, there
so I should not write down the concrete version. That's true. Yeah. Okay. So maybe.
You can define like this. There exists actually a unique V-bar.
Yes.
Such that there is an isometry in the morphisms from
Yes.
one to V tensor V-bar.
Yes. Yeah.
And this is V-bar.
Yeah. Okay. Yeah. Okay. So there is some conjugate. If we are in the Katz type, then this is exactly as I wrote down this Uij star. But okay, in general, that's true. I should just write it like this.
I mean, if you take finite dimensional representations instead of unitary, that will also satisfy all the properties, right?
I don't know. What about this? but I don't know if there's a problem for this one, but I don't know the details for that. Yeah.
V bar, that may not be unitary, that's what the problem.
Mm-hmm.
The problem of V bar may not be a unitary, right?
Mm-hmm. Yeah.
So if you just, from the start, you take all finite dimensional representations instead of unitary, then there is no problem in defining V bar.
Yeah. I don't know. Maybe it works, but I don't know. Yeah. Okay. So this is.
Is only one for which you have a container.
Yeah, that is the V bar.
Okay, so this is one part of the theorem, but of course if I say you can reconstruct it somehow from this representation theory, you have to go back, and this is the very interesting part, and this is his Tanaka Crying theorem. And it says, if you take any concrete monoidal W star category, so something like this, then you can associate a quantum group to it. So if you take any concrete monoidal W star category, such that some U exists and U bar generate R, in the sense that you use these properties to generate all the other elements from R, then there is a compact matrix quantum group AU such that R is its representation theory. Moreover, it's universal. So you have a homomorphism whenever you take another compact matrix quantum group such that it is a model of this representation theory. Okay, so this is the way back. So whenever we start with such a monoidal category, then we can associate a quantum group to it, and it is universal in some sense. Okay. So.
Can you possibly explain what it means to say generating?
Yeah. So it basically means you take this U and U bar and the tensor products, composition, involution, and so on, and then you generate these elements. There's some subtlety which I will now mention in the proof, because you have to take the closure, the completeness of this R. So you need some more structures here. But in general, you take this U and U bar and you use these properties and try to construct the other representations out of it. Okay. So as I said, I will. Maybe let me mention this now in the first step of the proof.
Excuse me.
Yes.
Does this definition have built into it the fact that everything is a finite direction of very reduced?
So, sorry, that you have a finite sum?
That everything is a finite direct sum of irreducible.
Yes, yeah, okay, you use this, yeah.
No, but is that apparent from the definition that you've given?
No, you have to work for it.
Huh?
You have to work for it. So I'm sketching these two results. I give only a very brief form of it. But if you really want to see the details, then you have to work for it to see that you have this irreducible, that you can decompose into these irreducibles. You first have to find, for in this abstract sense. Yeah, so let me say something about the proof. So if you take such an abstract object, then the first thing to do is you want to complete it. So this may be completed, which means we allow taking direct sums, equivalence classes or equivalences, and subrepresentations. And then so this will give the same AU in the end. And from this we can deduce that they are irreducible objects. Which I will denote by R irreducible. So this is, if you want to see the definition of this, you should take a look at proposition 2.4 of Voronovich's paper. So this is 24 is this one. This is the Tanaka Crying paper. And there you see that when you take such an abstract object, you can complete it. So you will allow that all these things also exist. And from this you can deduce that there are some irreducible objects, and that you can do this decomposition into irreducible objects. Does this answer the question a bit more or less, or?
In that sense, that it generates, right?
Yes, exactly, yeah.
All the irreducible pieces,
Yes.
Generation is something more because you take tensor products. Irreducibles you can just get it by direct sources.
No. You take tensor products and look at the irreducible components. That is what the generation means.
Yes. So
every irreducible will occur in that list.
No, I mean, yeah, sure. And then if you take any representation, it will break up as sum of irreducible. That's, but every,
No, but every irreducible representation will occur as tensor product of U and U bar.
No, it will be some representation of
exactly. So you also need this
of words. Of words in U and U bar, then you.
Yeah. So by saying that U and U bar generate R, I need to take tensor products of U and U bar, then pass to some subrepresentations. By this I will get the irreducibles, and if I take direct sums of these, I get all the objects. This is a precise way of stating what I mean by generate. Okay, and so once I have these irreducible objects, I can now define an algebra A0 as some direct sum of some linear functionals so these are the linear functionals on this B of HA. So I take these irreducible objects, they have some Hilbert spaces, and here I take the linear functionals, I take finite direct sums, and using the tensor product on R, we define a multiplication and this conjugate, this defines an involution. And then you take some supremum as a norm, sub over C star semi-norms yields a norm. So in fact it first yields a semi-norm, of course, but you can prove that there is some Haas state on this A0 and it is faithful, which gives us that this semi-norm is in fact a norm. So is a norm since there is a faithful Haas state on A0. And now completion yields my A. Completion yields my A, and this A0 sits inside the A exactly like we had in this theorem before, that this dense subalgebra. Okay, so as I said, this is very sketchy, and in the end we're not interested in how this A is really constructed. You just want to use that it is universal. But yeah, if you want to do it by hand, this is more or less the road to take. And yeah, by this means when we start with a quantum group, this these representations and the intertwiners, they form a category, and from the category I can reconstruct the quantum group. Okay. So this is very nice because this is now a way to produce.
There is some kind of addition to the objects in R and so on, right? To start with, you will give some examples of certain quantum groups from this thing, right? That there is a motion of addition on R.
Yes. Yeah. So here some direct sums. Yeah.
Now in that you have a general addition, but this is you're having a category, so you start with some objects and morphisms.
Yes.
It's a monoid. This R is a monoid. So there is
So that means there is a
there is identity, there is addition, and there is multiplication. Addition, yeah.
kind of
Yeah.
yeah.
Yeah. Direct sum is
Yeah, but it is direct sum is the addition in the rep G. But here he has to start with something.
Yeah. So
Addition.
yeah.
So abelian category or something.
yeah. I mean,
Category will be.
I guess that this is what I say in the proof. First, you take this R morphisms, and then you complete it. And with this completion, you allow these direct sums and so on. So in fact, this is so Voronovici distinguished between concrete monoidal W star category and complete concrete monoidal W star category. So yeah.
It's called a strict concrete monoid or something.
In Voronovic's paper, you mean?
Yeah.
No, I guess he calls it complete. I guess, but yeah.
There's something.
But I guess he mentions that in some category languages this might be strict or something like this. Yeah. So I wanted to simplify a little bit because otherwise the list would have been longer. So but when you have this, you also have this completeness, and then he has a theorem that if you start with the complete one, then you get all your stuff. But in fact, you don't need the complete one. This is enough. This concrete W star category, because you can complete it. Yeah. Yeah. So I mean, if you really want to go further into the details, then you should take a look at the paper. I guess it's pretty well written. So, but I wanted to not cover more than 2 blackboards for this theorem. Okay, but for us the main point at this stage is that this gives us a way of defining quantum groups. Okay, So whenever you find such a concrete monoidal W star category, you can associate a quantum group to it, right? And now if we take a look at these things, tensor product, composition, involution, well, this is something which doesn't look too complicated. And we will now mimic this in a purely combinatorial way. Okay, so I will now jump to chapter 4. I will introduce some partitions. I will introduce these notions on these partitions, and then of course we can associate a quantum group to it. Okay, and this is a very nice thing, because due to this Tanaka Crying, we can jump back and forth between the quantum group, which is a complicated operator algebraic object, and the combinatorics, which is seen as easier. Okay, so this is the next step now. So already in the Vodanovich paper on SUQ2, he uses some combinatorial ways of dealing with this quantum group, and then for describing some things about Sn plus and On plus, Barnica also used some combinatorics. So over the years, more and more some purely combinatorial structure was extracted. And this yields to these easy quantum groups, which is a quite new business. So this began in 2009. And this is the next chapter. Definition of easy quantum groups. And we just start with combinatorial objects. So a partition P in PKL is a decomposition of K plus L finite points K of which are upper L are lower into disjoint subsets the so-called blocks. And pictorially this means, for instance, we take two upper points, we take say 4 lower points, and we can, for instance, connect them in such a way, say. So here I have 2 upper points, I have 4 lower points. I put these two together in some subset. These two together, this one is alone, this one is alone. Okay, and I write this pictorially with these lines. This is just a way of saying how I decompose this 6 points into disjoint subsets. Okay, this will be a partition with 2 upper points and 4 lower points, or I could also have maybe this one this will be a partition with 4 upper points and 1 lower point. Okay. And the set of all partitions is denoted by P. So for all K and L, this is denoted by P, and we also allow that K and L are 0. So this will be our basic object for the next 4 lectures.
So K and L is 0,
that's allowed.
Specify, it's a distinguished point, that's all.
This K and L?
K and L are 0, there are no points, so you should
Yes.
call that partition as some kind of distinguished partition.
If both is 0, you mean?
Yeah.
No, if both is 0, we just call it the empty partition. Yeah, yeah. We give a name to it, maybe. Yeah.
Is it not necessary to distinguish between the upper and the
It is necessary. Yes.
And also, let's say the points are numbered, they're distinguishable.
Yeah. So I can number them. So often I will omit the numbering, but I can number.
No, but they're not
The order is important. That's true. Yeah. Yeah. So if I want to write it just as a set, I need to have the order of the points. But we will mainly use this pictorial representation. Okay. So we just write k upper points, l lower points, might be 0, and then just connect them with some lines, which gives us some subsets. Okay. And now once we have such a partition, we can form another partition by taking, for instance, the tensor product, which is we take one partition and another one, and we define the tensor product simply by is obtained by placing P and Q side by side. So here, this will be our toy example here. So I take the first one, and I take the tensor product with the second partition. Then this will give a partition with 6 upper points and 5 lower points, just by putting it side by side. Okay. Okay. So this is one of the operations we can do. Next thing we can do is composition.
The empty partition to have a multiplicative identity, right?
The empty partition?
You need one tensor u equals 1.
Yes.
So you don't place, you need the empty.
Okay, yeah, so okay, so you're speaking of this category sense later on, yeah. So this empty partition, we can just call it the empty partition, and then of course if we take the tensor product with it, it yields the partition itself, right? Yes. Okay, we also need composition. This is the next thing. So if P is from K to L points, Q is from L to M points, then the composition is from K to M points, and this is obtained from placing P above Q and removing the middle points. Here certain loops may appear, and they will play a role later on. So let me say in this example what the composition is. So I take one partition and I take the other one. And of course, in order to compose two partitions, I need that the lower points of the upper one is the same number as the upper points of the lower partition, right? So what do? I just follow the lines. So this is, I have two upper points now and one lower point. So this upper point is all alone. The second point is connected with the lower point. And that's it. And these middle points. So say it again.
Partition in what sense? What
The
does picture signify?
so this is a partition in a set theoretical sense. So this means I have a set consisting of 6 points. I want to decompose it into disjoint subsets, and these lines, they represent which subsets I take. So if you want, I could also write it maybe let me call these lower points with primes, for instance.
Line is a subset.
Yes, is a set.
And this is not a line. This is that 3 dash and 4 dash. What is that?
This is also a line. So 3 and 4 are
Set
connected.
containing, that's one block.
Okay.
That's one block of
Set
one.
containing 3 dash and 4 dash.
Yes.
Okay.
So if you want to write it as a set, you could write it.
It is not like a line. What is the speciality of this?
Ah, okay. You mean why don't you write it like this? Okay, this is just aesthetics. Aesthetics. We find it nicer. No, we will see later that it makes more sense to use
No,
a
like
bit
when
more.
you stick them together, you have two identical things.
Mhm.
You don't distinguish them.
Here in the composition, we would have something like this, and it would be not so clear what to do with such an object. Yeah. So, for instance, it could be when you do the composition, you have something like this, and from the lower partition you have something like this, and then you have again like this. Okay, so it's easier to follow the path if you write it like this. But you could also use things like this or like this. So that's up to you.
He will say if you have, if you have drawn it straight horizontal line, you could have just drawn in a line instead of going like this.
Yeah, okay.
Much faster.
Yeah. Okay, so this is composing these partitions, and okay, so somehow, I mean, this is a dead end, but it doesn't bother us. So it's in the middle point. So we are only interested in taking the upper points, taking the very lower points, and then just following the lines. It's like a game, okay? And here you see you have here 2 middle points, and they are not connected to anything else, right? So we just remove it, and this is a loop. Okay, and in a minute we will see that we need to count the number of loops for a certain thing, but at this point, for the combinatorial thing, we just remove it. Okay, we also have involution. This is simply by turning P upside down. Or if you want, you reflect it at the horizontal axis. So in our example, the involution of this partition would be this partition. Mm-hmm.
But if you oppose this with, let's see, another one at the bottom, just write down this one time program, repeat this thing as it is, and then below that you draw one with 4 on top, 2 on the bottom, okay? And then suppose you, or maybe even 0 on the bottom. And suppose you link 1 and 3, and 2 and 4 are singletons.
2 and 4 are singletons, yeah. Yeah.
Then it is receiving called it a loop, right?
That's true.
Huh?
That's true.
So, but still you throw that away, right?
Yeah, yeah. Yeah, so, okay, maybe you could also call it, I don't know, middle blocks or well, so some connected components on the middle row, on the middle points, right? Yeah. Yeah, that's true. It's I heard it before that loop might be misleading, but so far I didn't find a better name. So maybe removed blocks or.
I mean, the top is x is related to z. If there is a y, is related to x and z. Is that the composition of?
This one here?
No. X can be related to Y1, which can be related to Y2, which can be related to Y3, which can be related to Z.
You can have some quite complicated things. You mean something like this, right?
So but Y1 is limited to Y2 means or what? Yeah, that's what I'm saying. So the top, middle and bottom points. Top points you call it as X. Middle points you call it as Y, and bottom points you call it as Z. So partition means giving an equivalence relation. So X is related to Z if there is a Y, such that X is related to Y and Y is related to Z. Is that what your picture says?
If you want, probably you can formulate something like this, but we don't need such formulations here, I guess. So, I mean.
What,
So of course, you can define. You can do a lot of things with these partitions. You can define such equivalence relations. You can also, if you have the same number of points above and below, then you can form an algebra on it. So this temporally leap algebra. So you can do a lot of things with these partitions. But here in this business with the quantum groups, we only want to have this concrete monoidal thing. And for this, we only need these operations. Okay, so let me define what a category of partitions is. Namely, this is a subset C of P. So this consists, to be more precise, consisting of sets CKL in PKL for all K and L. Okay, so this is a category of partitions if it is closed undertaking tensor product, composition and involution. So if it is closed under B, C and D, and if the identity partition which is the partition just connecting one upper point with one lower point, if this is in C, and also the pair partition. So this simply connects two lower points. Okay, so this is my category of partitions. We just take sets of partitions which are closed under these operations, and the identity and this pair partition is in my category. So let me now give some examples. Maybe for writing down the examples, it would be nice to have this still here. Okay, I guess the tensor product is not so difficult. Can you erase this? So example, P is a category, the set of all partitions. Okay, this should be the case, of course. If you do all these constructions, tensor product, composition, involution, and so on, with partitions, you obtain a partition. So this is why P is a category. Second, the set of all non-crossing partitions is also a category. So this means lines may be drawn in such a way that they do not cross. So this is also a category of partitions. Okay, so far I only draw non-crossing partitions, but for instance I could have something like this. Maybe this point is connected to this one, these two are connected, and also this is connected to this one. Okay, here you see that these lines cross. So this is not a non-crossing partition. Okay. So if I can draw these lines such that they do never cross, then it's a non-crossing partition. Otherwise, it's not. No. You have to go in between these two. Yeah. Yeah. So some people like to draw this on a circle. Okay. So these are the non-crossing partitions. They also form a category. Okay. If I take two partitions which are non-crossing, I put them side by side. Of course, it's still non-crossing, right? How can a crossing happen? And also with the composition, if I go from above to the middle points without crossing a line, then I go to the lower points without crossing a line, then this is non-crossing in the end. And if you flip it, okay, this doesn't change anything. Okay, so this is also a non-crossing. Then these non-crossing partitions, they also form a category. And you can convince yourself that there are two more very natural categories. So the set of all pair partitions so all blocks are of size 2. They also form a category. And likewise, if you take the non-crossing pair partitions. Okay, let us think about this for a second. So all blocks are of size 2. Okay, so yeah, something like this. I don't know. This, for instance, could be a pair partition. Okay, and this one, of course, this is not. Yeah. So you always only connect 2 points. This is these pair partitions, if you put them side by side, okay, still it's only always connecting 2 points, right? So the tensor product is clear. As for the composition, if you have 2 points on the upper line, if they are connected, then they will also be connected in the composition. This doesn't change anything. Otherwise, you have maybe one upper point which is connected to one point in the middle, and this point in the middle then can either be connected to a lower point or it can be connected to another point on the middle. And then you have to check where is this again connected and so on. So you have to chase a little bit around with these points, but in the end you will always see when you have pair partition, you compose it with a pair partition, you end up with a pair partition. So nothing strange happens. And involution again, that's trivial. And these 2 partitions that I wrote down here, they only connect 2 points. So these are pair partitions. It's okay. So this also forms a category, and if you do this in a non-crossing way, this is also a category. Okay, so these are 4 examples of categories of partitions, which in fact will play a natural role in the sequel. Is there a question so far concerning these examples? Okay, so I will try to give at least a definition for the easy quantum groups today. Namely, what we now need is how to come from these partitions to linear map, which will be the intertwiners. So we need to associate a linear map to such a partition, and this is done in the following way. So we take a partition and we define a linear map from the nth power of the complex numbers, and this to the kth power, to the to the other space. So as the linear map.
For each n, you get one of these.
Yes, yes. So I choose an n and then I proceed. Yeah. And this is the linear map given by Tp of ei1 tensor eik. This is mapped to delta Pij, ej1, ejl, where E1 to En is an orthonormal basis of C to the n, and I is just an abbreviation for this multi-index. What do I mean by this delta? I mean the following. So if you have this vector space over here, these elements, of course, they form an orthonormal basis, and now I just have to explain where they are mapped to, and this is all the possible choices they have, and there can be some coefficients, right? And what are these coefficients? These coefficients. Sorry. This one? Both are n, yeah, sorry. Yeah. Both are n, yeah. So these coefficients, delta, they depend on the partition and also on the indices. So delta Pij, this is 1 if I write down all the indices. So I write down my i's and my j's, and I check whether my p connects only equal indices to equal indices. If this connects only equal indices, and otherwise it's 0. So maybe an example, if I have my indices I1 equals 1, I2 equals 3, and then I have 4, 4, and I have this partition, then here I see, yes, I4, yeah. Thanks. So here I connect a 4 with a 4, that's okay. But here I connect a 1 with a 3, that's not okay. So delta is 0. If I, on the other hand, if I have something like this, then my delta would be 1. Okay, so I just write down my i's, I write down all choices of j's, I check whether my p's connect equal indices with equal indices. If it is so, this vector is in the sum, otherwise it doesn't appear in the sum. Maybe let me do an example of such a map. Namely, let P be this partition connecting two upper points to two lower points in a crossing way. Then I apply my TP to EI1 tensor EI2, and this is now the sum over all such elements. Okay, what's happening there? I take my I1, I take my I2, I take my J1, I take my J2, and now equal indices must be connected to equal indices. So the only choice for J1 and J2 that survive is when J1 is I2 and J2 is I1. Okay, so this is the only vector that comes out is this one. So this is the flip map. Okay. Or another example, if you take this identity partition, then TP is the identity. Okay. So this index must be the same as this index, which means it only maps EI to EI. Yes. So this comes now. This is the next proposition. Yeah. So far we just associated this linear map, but as you said, this functor mapping a partition to such a linear map, this behaves very nice with respect to this operations on the partitions. Otherwise, we wouldn't have chosen this mapping from P to TP. And in fact, it looks like this. Maybe at this. Say it again, please. This one does not?
Equal in this means I1 will J1. I1 will
Yes. Yes.
J2.
So here.
I1 and J2 are equal.
I1 ranges from 1 to n.
Put those index values. I1 I take a 1 to n number. So put those index values and all this will be same.
Yeah. So you choose an arbitrary I1 and I2. Yeah. Yeah.
I1, I2 varies from 1 to n.
Yes. So maybe at some point I should mention that this all this theory was developed by Theo Barnica and Roland Speicher. I will mention this when I give the definition for an easy quantum group, but also this was all developed in their paper from 2009, and also there can be found the following proposition, namely we have that TP tensor TQ is the same as TP tensor Q. Also for the composition, we have that this is TQP, so I leave here some space, and the adjoint is just the adjoint of the partition. So as for the composition, life is not as nice as it is here, because you have a factor to take into account, and that is exactly these loops that appeared when we have such a composition. They must be mod out. So these number of connected components around the midpoints which you wanted to remove, this must be counted and must be taken into account for this composition rule. And to this number. The number is called, it's an R, yeah, removed loops.
Oh, I see, removed loops, not R times N.
No.
Oh, I see. So okay, fine, no problem.
Yeah.
That number of loops.
Yeah, maybe I should write it like this. Yeah, that's true. Yes.
Basically, you take, is it same as the saying, take a vector space with bases as partitions and multiply them according to the loops?
Yeah, you can define such a thing directly on the partition space. Is what you mean, right? Yeah.
No, but you are allowing yourself that parameter, and partitions don't have an n inbuilt into them.
Yeah, I understand. But if you multiply,
So you somehow.
How do you multiply them? You must throw it a weight.
yeah. So if you define the multiplication like that, like n power something.
You must pass from the partitions to some maybe group algebra over the partitions or something like this. So you
formal sums of partitions.
Exactly,
and
yeah.
Let one partition act on by multiplication. Is that the rule that you?
You could do such things, yeah. I mean, this is not what we are doing here. We're doing on this in a concrete way on a Hilbert space, but you could do something like this, yes. Okay, so maybe let me just say a little bit about the proof. So this can be checked directly. So just write down the formulas, and then it's pretty immediate that this is true. But let me just give an example for this B and explain how this strange factor comes in. Okay, so but here's an example for B. Here's an example for B. So again, we take our favorite partitions. So we take this P and this Q, and now what happens if I apply TQ TP to EI1 tensor EI2? So this will give us some fourfold sum from J1 to J4, and I have some delta Pij, and then I apply my Q to it. And then my Q now has 4 upper points and only 1 target point. So here I only have an S, maybe S1. And it looks like this. Okay, I just applied the composition, and now I want to express this in terms of some delta of some partition, and of course now delta Pij, this is the same as, well, so these expressions, they are only 1 if, okay, what needs to be true? Well, J1, so okay, maybe I should write down the composition picture again. Okay, so this is 1 if J2 equals I2, and also on the same side J2 must equal J1 and S1.
So J3 equals J4.
This also comes at, yeah. So here first we have so we have this equation and J3 equals J4. Okay. So from the first thing we have that I2 must be equal to J2. Then from the lower partition we know that J2 must be equal to J1 and also must be equal to S1. And here both partition yields J3 must be equal to J4. Okay. So this is of course the same as saying I take the composition and I compare I and S. Is it okay like this? Is it okay? Okay. So of course now in this composition, what do I have to check here? I have to check that I2 equals S1. This is what is written here, and this is I2 equals S1. Okay. So this is the same index rules. But what about my J's? Well, my J's, J1 and J2, they are fixed by this I. Okay. But here for this J3 and J4, they must be equal, but I have arbitrary choices. Right? Okay, so J3 and J4 must be equal, but I have arbitrary choice. And this is how this n comes in. Okay. So I have n arbitrary choices for J3.
J4 has to be equal to J3.
Yes. Yeah. So in principle, here I have all the sum over all J3 and all J4, but J3 and J4 must coincide. But for J3 I have arbitrary choices. So this is where this factor n comes into play.
Why does J3 and J4 coincide?
This is from here,
Okay.
or from here as you want. Okay. So this is nice because now we have that this, if C is a category, then span TP, where P is in C, this is a concrete monoidal W star category. With maybe this abstract R, we just call these objects as the kth power of U, and this is generated by U, and U bar is the same as U, and we have that this is true. Well, what's it? Well, no, that's rubbish. I mean, just check the axioms. No. So sorry. I use this one. Yeah. Sorry. Use just an abstract object. So I mean here we just name the elements in R like this. You could also just take the natural numbers if you want. So this is maybe if you want it's clearer if you define R as
natural numbers and morphisms or partitions.
Yes, you can do it like that. Yeah. Or you can give name to you take some elements indexed by the natural numbers, and I just call them like this. Okay, so if I consider this span, that's clear that this is closed under the tensor product just by this proposition. It's also closed under the composition, because if I take the composition, I have a factor here, but I take the span, so it doesn't matter, right? So I'm still in the span. And same for the involution. So I can check that this fulfills all these properties of this monoidal category, and yeah.
Do you need a special element in your definition of monoidal category?
No. So I don't need it for the definition, but I need it for the next step to associate a quantum group to it. So in order to apply this theorem that when you have a category you can associate a quantum group, I need such an element which generates it. Yeah. So this is why I already stated in this proposition. Yeah. So now I can associate. Yeah. So it's a bit. It's just a name. It's a bit. I admit that it's strange to write it down like this. So let's say you can call these objects with some name which are indexed by this k, and this is you just call you have another object which you call u bar, but it's the same as u. So it's a bit strange written down like this. That's true.
You have to give morphisms and objects and morphisms. objects are natural numbers and morphisms are.
No, objects cannot be natural numbers. You have to have more than the natural numbers. It cannot be just natural numbers. Like also the simple objects. They are irreducible objects.
Yeah.
No, not even irreducible. This is like, I mean, you're taking one representation, taking tensor powers. Okay, they're not all the objects in the representation category. There will be sub-representations and all that. So you cannot just say that they're objects of this form.
Yeah. So this is this thing with taking the completion of the category. So I start with this. My R is just the natural numbers. My morphisms is just this. But then I have to take this completion in order to really get the quantum group and to think of this quantum group language. But as Voronovich proved, you don't need this completeness. So if you start with this, then you take the completion and will yield exactly the same object. Okay. Okay, so let me see if I can write down the next statement in time, or maybe I will shorten it a bit. So to each category of partitions, we may associate a compact matrix quantum group G equals AU, where A is a universal C-star algebra generated by UIJs such that TP U tensor K is U tensor L TP for all P. Yes? Yeah, okay.
This U bar has an intrinsic meaning when you talk about these W star categories, right?
No, I mean, okay. So in order to use the next, okay, maybe it's not a good idea that I wrote it in this proposition. Maybe I should do it in the proof of the next proposition.
If I understand correctly, you are describing a category.
Yes.
To describe a category, forget about U equals U bar. To
Yes.
describe a category, you need to specify what are the objects and what are the morphisms.
Yes.
The objects are natural numbers,
Yes.
and the morphisms are.
Actually, there are not natural numbers.
That's the point. I mean,
They are like
more.
Hilbert spaces.
Yeah.
U, if you want the Hilbert space, is C to the N. Okay? This is Hilbert space, C to the N. This is U. Okay? And then,
Okay, objects are C to the N tensor
if
K.
you want, you can see like this. Objects are Hilbert spaces. U corresponds to C to the N. U bar is the same, C to the N. And now, each time you have, let's say, a morphism here, let's say a non-crossing partition from K to K.
ATL.
Okay, do the morphism from U tensor K to U tensor K. This is the span of the TP, and you see by this that this is the C-star algebra, and each minimal projection in this will correspond to Hilbert subspace of C to the N to the power K. Okay, and this would be an object, an irreducible object, this Hilbert space. Each minimal projection in this C-star algebra. And like this, you have all the irreducible object which generates the category. Then the rest is direction of this. And the morphisms between the Hilbert space, they are given by cutting this span here by the projection, the minimal projection you have to the one I mean. And this is the technical, this is the completion he explained, this is the technical stuff.
You have not defined it.
So U means C to the body.
Yeah. Yeah, you can do object as Hilbert spaces, and U corresponds to the Hilbert space, and U tensor K corresponds to the Hilbert space C and the power K. But also any projection which is in the morphism from U tensor K to U tensor K, this is the C-star algebra, corresponds to a Hilbert space which is the image of this projection. This projection will act on the n to the power k. It will be the image of this projection when you go to an object. So we generate an object like this by looking at the image of projection in this span of.
Yeah, so maybe it's better to, as you said, to maybe denote the elements like this. But so I mean the thing is, you take an abstract category and this abstract morphisms, and then in order to see that this is really the representations of a quantum group, you need to do this completion business. You need to complete it, and by this completion, you get the sub-representations, the direct sums, the irreducibles, and so on. And then it's much more than just this. But Voronovich's theorem says you just start with such a thing, and you will get a quantum group. So on the way to it, you have to complete it in order to get the representations, but you can just start with such a category without the completion. And this is...
Okay, without the completion, the objects of the category without the completion are C power n tensor k.
Yes.
The morphism between C power n tensor k to C power n tensor L is dp.
Yes.
Now, who determines what n is?
N for every n, there is a category.
And then the process complete this projection in this image of projection.
Yeah, there's TP by itself starts with n. So
W star category.
here in this case, he's starting with an n. TP itself is defined by that Cn. So this n is fixed.
Yes,
If
the
I
n is fixed.
will get a different thing.
Yeah, so the n is fixed. So in Voronovich's theorem, you always get a compact matrix quantum group generated by some uij with a certain n.
Right, exactly.
So in fact, Voronovich's theorem is you get a series of quantum groups for each n.
You get a category.
No, but my understanding was that a category C was a subconnection CKL or PKL for every KL, which was closed under this
There are
product.
too many categories floating around.
There's
there.
no n there, right?
Yeah, that's true. There's no n there. That's true.
So he should write Rn probably.
Yeah.
With Rn equals
Yes.
Rn comma C. If you got.
Yeah. So okay, this is a bit confusing thing, and we will speak about this next time. So when you have this category of partitions, this is really there's no n involved, but and also this is not exactly the representations of our quantum group. But to this category, to each n, we can associate this monster, and then we get a quantum group associated to it by completion, and then the completion will give all the representations and so on. But Voronovich just says, okay, give me this one, and I will give you a quantum group. If you don't care the pre-says how I get it, then just give me such a category, and that's it. So for each n to such a category of partitions, to each n we will get a quantum group, and this will be the definition for the easy quantum group. Okay, but I will repeat this next time.
Why did they introduce this thing at all?
This
What was the reason, yeah? Voronovich,
this category of partitions.
yeah.
So the reason is that this is a very nice path of seeing of getting quantum groups. So for instance, this Sn plus and this On plus, these are important examples, and they can be seen as coming from this machinery, and you get much more, which somehow, if you want, look like Sn plus and On plus. So if you want to have more examples which are in the philosophy of Sn plus and On plus, this is the road to take. And so in my work during the last 2 or 3 years, I classified all these quantum groups coming from it, and I could show that there's a huge variety. There are a lot of examples, and in some sense we try to understand all the compact matrix quantum groups by first understanding the easy quantum groups, and then transferring it to the quantum groups. So I will speak a little next time a little bit about.
Does that mean that are you hoping for some structure theorem for compact quantum groups in terms of these objects?
Yes. So there are some things which we can already do. For instance, representation theory for these easy quantum groups, this can be expressed purely in terms of combinatorics. So you can understand representation theory just in combinatorial means. And also we have another theorem. You have some theorem for the easy quantum groups, and we proved it in terms of this combinatorics. And in fact, it turns out that this holds true for a larger class of compact matrix quantum groups, not only for the easy ones. But why we have this result is just because we analyze the combinatorial structure. So we hope to have more results like this, that we understand the combinatorics. We prove a result for these combinatorial quantum groups. We see that it holds true for other compact matrix quantum groups, and by this we understand more about compact matrix quantum groups. This is somehow the philosophy. Yeah.
These are all cats.
They are Katz type? Yes, they are Katz type. Yeah. So this is because of this functor TP. Yeah. So if you modify this TP, then you will get non-Katz types.
No. But this second category is the WS concave one or
Giving a kind of you're just giving a basis to build a category, right?
Yes.
It's enough to complete it.
Yes.
You have not defined what the direct sum is and so on.
No. No, I'm
take direct sum and say projections.
Exactly. This is much more complicated. I mean, I did this with Amaury Frelon when considering the representation theory of these things. But yeah, as I said, if you just start with such a simple thing, then there's some completion in the back, and this will give you a quantum group. But yeah, the nice thing is that you do not really need to understand the completion at this point in order to get a quantum group. Okay, thank you.